So in part one of this video, we're going to be talking about shift graphs, and it's very similar to how we think about Michelsky construction, or at least that's what we're going to try to do. We're going to try to connect this to Michelsky construction. So we're going to start with a really simple case with n equals 2. So one of the important things about shift graphs is that edges are actually vertices. And so to start this, we're going to lay down points. I'm going to call them points because I want to distinguish points from vertices. Again, vertices will now be edges, and points will, I'm just going to call them points as something used to construct these vertices. So if we think about this, we're going to connect them with curved edges. So to create a vertex, I'm going to connect this point with this point. And so now this curved edge that you see right here, this curved edge is actually a vertex. It's not a curved edge. We call it that in normal graph terminology, but in a shift graph, this now becomes a vertex. And similarly, if I want to form an edge between this point and this point, I can do this. So now, in this graph, in this shift graph G, with vertex size n equals 2, I've just shown that. I have two vertices. If we recall the Michelsky construction, if I scroll down here real quick, if we recall, we have this additional point here that's adjacent to all the vertices in an independent set Y. And why do we have an independent set Y in this additional point? Well, we wanted to increase the vertex size from n to 2n plus 1. So if I go back up here, right now I have n equals 2. So first I need to double it. So what I'm going to do is I'm going to lay down 2, 3 points. The first step is to double it, and then to have this last point here to form all edges, all of these being independent, and then forming all these edges. So what we're actually going to do is we're going to have this semicircle form here. So this will be one. That's an edge. That's a vertex, rather. This is, if I go back real quick, that may take some time to load. We go back. Essentially, what I want to do is I want to do the same process of creating these vertices. Whoops. So again, all these edges are now actually vertices. So this is a vertex. This is a vertex, and then I'm going to have this one right here. This is another vertex. So I have these three independent vertices. So I can think about this now being my independent set Y. And then I'm also going to have this edge over here, and I want to connect all of these edges. I want to connect all these edges with all of these vertices in the independent set Y. So how am I actually going to do that? Well, I can take this point right here. I'm going to connect it with each of these. So here we go. 1, that forms a connection there. 2, this forms a connection. 3, this forms a connection. And so let me just scroll down real quick. So this is where it gets difficult to use the Michelsky construction with working with shift graphs, because then it's like, well, is this a vertex? And if so, then are they independent? Are they dependent? When we only connect one point from one other vertex, I'm going to label this an edge. And you really have to at this point, because you have to specify an edge from a vertex. This will be an edge, this will be an edge, and this will be an edge. And so in our project, this was the most difficult part, because when Dr. Trotter explained shift graphs, there was no relation to the Michelsky construction other than that it had some sort of relationship that between the increase of vertex size and the achromatic number. But what we're really saying is if I draw an ellipse around this original graph, this will be, what I'm saying is this right here, this ellipse that I just drew around. And let me actually delete this point. Let me delete the ellipse. Yeah, it does. Okay. What I'm saying is this is the original shift graph G. This is n equals 2. These are two vertices, and they should be independent. So what I'm going to do is I'm going to have a second point here. Actually, no, I'm going to delete. Sorry, I'm going to delete this point. delete this point, and I can go ahead and redo this, these two vertices. So here we go, 1, and then 2. So now these are independent, and this is my original graph G. These should have neighbors, and so each of these neighbors will be points as well, but remember, they're going to be these edges. They look like edges, these curved edges. And so these would all be connected. Now, if we think about it, this poses a couple problems because this is, if I label this as X, which is the current vertex that I want to think of, it's not a permanent value, it's just a floating assignment. That way we know which vertex that we're working with. If I think about this as X, we see a problem because if I try to connect these two vertices, then it looks like I'm forming another edge. And that other edge, that additional edge would then be, in the terms of shift graphs, would then be another vertex. And so we get into this conundrum of trying to connect these vertices with edges, and those edges then being vertices. So in order to remedy this, what we came up with was connecting just one point from each edge, if you will, but really each vertex, with a straight edge, indicating this is not a vertex, this is an edge. And so really, we can think about this as a pseudo-shift graph, where instead of having all edges in a normal graph now being vertices, we're going to have most edges now be vertices, with the exception of straight edges being legitimate edges between two vertices. So these are all in the neighborhood of X, and then these would be in this other neighborhood. And then when we try to connect this X, if we try to connect, or at least relate it to this independent point over here, what we find is that we're going to have the same thing from the previous Minkowski construction. What we're going to do is we're going to connect this vertex over here, denoted by this curved edge. We're going to connect it all the way over. We're going to connect it all the way over to one of these midpoints, if you will, which will be, this will be connected over here, and then this one will be connected over here. So we have each independent vertex in the independent set Y being connected to each vertex in the neighborhood of X. And so actually I'm going to delete one of these edges because I only want to focus on one. And so this can be, this one doesn't matter. Okay. So if we think about this right here, these two edges are really going to be edges instead of vertices. Now that we've done this, we would do the same color assignment that we've done in previous times with the Minkowski construction. But before that, I still have to connect. So this vertex in the independent set Y is adjacent to X right over here. But it is not adjacent to the mate. So there is a mate over here, and these are all mates for X. And so if we were to do that for each one, we'd connect it here, we'd connect it here. And so if we try to do the coloring now, we start with this being colored alpha, we color this other one with alpha, and we color this independent, or this additional one, X naught, with alpha. And actually, I can even specify it being X naught real quick, like we've done previously. So this is X naught right here, this curved edge. And so really, I can go back, I can delete this, since I said that these would be edges, and I said that I would define legitimate edges in terms of shift graphs with straight segments. It would be connected in this fashion. Let me actually pull this down so you'll be able to see. So it'd be connected in this fashion. Here we go. This segment attached to here, here, here. Don't mind the edge crossings. Those would not be existent in a full demonstration. So this is an edge. It's an actual edge. This is an actual edge. And this is an actual edge. And so if we were to do the coloring again, we'd find the same thing that we did with the regular graph, which is that if we have this vertex right here, and we color it alpha as well, and so we can color this alpha as well because it's in the independent set Y and it's not adjacent to these. If we were to let's say, here we go. This would be alpha. If we were to do the color assignment again, we would scratch out this alpha and we'd turn it to a beta. And we are going to say that none of these can be alpha, right? If I try setting this as alpha like I just did, we find it can't be because there's an edge connecting x naught and a vertex and independent set y. They'd have the same color. Can't have two colors adjacent to each other, so this cannot be alpha. We're going to call it beta. And so I'm going to delete this alpha. I'm going to delete that alpha, and actually I'll just move it off to the side. This is now beta, which means that all of these would remain alpha. And so we find that because our original coloring was, if I do chi of g, the chromatic number was originally t. Originally for this graph, we now find that it must be t plus 1. And that is because we do the color assignment again, changing alpha to beta. And why do we do that? Well, we look back to the x naught case. We see that x naught is adjacent, which means it has to have a different color assignment. And this addition of beta, which was not already in the range of colors from 1 to t or a to t, does not matter. To some range of colors with size t, beta was not in that original range. We add that in. That's why we get our plus 1. So shift graphs are really useful in that not only are they really unique, the fact that edges now become vertices, but it was really interesting trying to apply the Mikulski construction to shift graphs, because what we found was that we'd actually have to create pseudo edges where we're basically saying while this should be a vertex in shift graph notation, we're going to keep it an edge. And so while that does it does violate some properties of shift graphs in a sense, we had to have this in order to actually proceed with the Mikulski construction. So what we learned from this was really, yes, you can perform a Mikulski construction of shift graphs if you really are working with both hands tied behind your back, if you really completely change the notion of an edge being a vertex for some of the vertices, those being the ones connecting the x naught to all the vertices in the independent set y, and as well as all the vertices in the independent set y being connected to the floating assignment x, which is just a current vertex in the original graph G. And as you can tell, this was pretty complicated just for vertex size n equals 2, but with n equals 3, n equals 4, if it's increasing to, and I'll write this out, if it's increasing, if vertex size increases to 2n plus 1, which is why we get the new chromatic number of t plus 1. Just imagine if we had a vertex size of 4. 4 times 2 is 8, plus 1 is 9. It gets fairly hefty later on. So the best approach for this would be to have an algorithm that would actually be able to use not a first fit necessarily, but some sort of concept-related first fit to color the shift graph. And coloring shift graphs is something that we really haven't covered, and that's something that we wanted more explanation for and more exploration in our project, something that we didn't really get to do yet. But the greatest takeaway from shift graphs and relating to the Mikulski construction was that by increasing the vertex size to 2n plus 1 and changing our notion for some cases, those being the connections between x naught and the vertices in the independent set y, changing those to edges and not being vertices. If we do that, we do see that the chromatic number does increase to t plus 1, and that should make sense. So if you scroll all the way back down here to the original Mikulski construction, we find that we were able to increase the chromatic number to t plus 1. And again, the purpose of Mikulski was to show you actually can color it with t, but then prove by contradiction. So this entire project dealing with or at least this portion of the project dealing with Mikulski construction was basically highlighting and showcasing how we can prove things with contradiction. And the greatest thing the most important thing when using contradiction as a proof mechanism is to realize we have to have grounds for contradicting. And in this case, the grounds for contradicting was the fact that we had to create pseudo edges where in the shift graph terminology, or normal shift graph terminology, it really should have been just a vertex.